So we're going to learn how to find the probability of A union B. What does A union B mean?
A and B.
It's A or B. That's the same thing as saying probability, of A or B. So make sure you understand, because that's going to change how you approach a problem. So probability of A or B. So let's do a little Venn diagram, and I'll kind of show you what that looks like. And that's not what I meant to do. Okay, so I have our Venn diagram here. If I have event A, whatever that may be, and event B, whatever that may be, where is my A in union with B?
It's the entire diagram.
It's this entire part right here, correct? All of this. So that means A or B could contain elements in A but not B, elements in B but not A, or elements that are in both. So that is how that works. That's what that looks like. So if you're finding the probability, you would find the number that are in any of the shaded regions, divided by what?
The ones that aren't in the shade.
The ones that are not in the shaded region but are out here in the sample space, or in the universe, the universal set. Okay? So let me give you a formula. Probability of A or B is equal to the probability of A. Now, do you think we're adding here or multiplying here? When we do A and B, what do?
Multiply.
When we do A and B, we multiply. So what do you think A or, did I just say that backwards? When we do A and B, we multiply. A or B would be adding. Okay, I know this is the silliest little thing, but a student of mine said, this is how I remember it. Or addition. Or means you add. You do addition. Students cannot remember it. I know. Just remember the word or addition is kind of strange, so just remember it. So I'm going to add probability of B. Now, there's a little trick. You have to subtract out any overlaps. Isn't that weird? You have to subtract out any overlap. When I do an example for you in just a second, you're going to understand that. Now, this is our new formula, and this means you subtract the elements that are in the intersection. Or it could be the probability of the elements in the intersection. So I'll show you how to do that. We're going to do an example, okay? So that is our new formula, and let me kind of show you what we're going to do with that. So here's our first example. I don't know the probability, if I have a deck of cards, of getting a face card or a red card. Okay? So we're going to use our formula. That's going to be the probability of, and I'll just call this F. You all with me on that? And then I'll call this R. So I know the probability of F plus the probability of red, which is a red card. But I also need to subtract out the overlap. Okay. Before we dive into that formula, let's do a Venn diagram. This concept really lends itself nicely to the Venn diagram and understanding what you're doing. So let's do a Venn diagram. So you guys know what a Venn diagram is. It's just one of the tools we've been using. And it also kind of helps us see the universal set and all that good stuff. So I'm going to have F for my face card, and then I'm going to have R for my red cards. Okay? So I need to know how many face cards I have. 12. That's exactly right. So it'd be your jacks, your kings, and your queens for what?
4 suit each.
For each of the 4 suits. So 3 times 4, you do 12. Do I put a 12 right here in this spot? No, why do I not?
Because some are red.
Some of them are also red. How many are also red?
6.
6. So these are my 6 red face cards. These are my 6 black face cards. But do you see that the event of having the event face cards, there are 12 elements. There are 12 cards that meet that criteria. What about reds?
26.
No, because 6 of them are already.
Okay, there are 26 reds, but I already have 6 inside the red bucket. So if I kind of think of it like this, let me kind of show you. These are my reds. I already have 6 in there, don't I? So I have to put 20 here. So every time you design a Venn diagram, you set it up, ask yourself, is it correct? Do I have the right number of face cards? Yes, I do, 12. Do I have the right number of reds? Yes, I do, 26. And then those that are both red and face cards go in the center, go in the intersection. Now I need my universal set out here. How many? Because there's 32 right here, correct? So wouldn't it just be 20? Okay, sometimes you'll have some that are in the universal set that are not in either event. Sometimes you won't. It just depends on the scenario. Now, so let's use our formula. So there's 52 cards total. So if this is my deck of cards, and I'm basically talking about that deck of cards, I need to account for all 52 cards, right? And the descriptions and types of cards. So far, are we good? Okay, so what is the probability for a face card? 12 out of 52. What's the probability of a red or for a red? 26 out of 52. So is that my answer?
No.
Minus 6.
I have 6 over 52.
I have to subtract the 6 over 52.
Oh my gosh.
So that is going to be what? 32 over 52. Now, if I physically count the 6 plus the 6 plus the 20, there is my 32 right here, okay? So it's giving me this 32 right there, 32 out of 52. So the Venn diagram, could I have just used the Venn diagram and said, oh, I have 6 face cards that are not red, 6 that are red, and then I have 20 that are reds that are not. Could I not just added 6, 6, and 20 and still gotten to the 32? Yes, I could have. And this is what students make the biggest mistake on. They don't know how this formula right there relates to this Venn diagram. Okay? Now, what I'm going to do, is everybody with me? I feel like I lost some of you. Let's do a table with this Venn diagram information. So a two-way table we're going to do now. So go ahead and start setting it up. Let me kind of show you.
Do you have to simplify, or can you just keep it like that?
I do want you to simplify, but
Okay.
that part I feel like y'all can do. So I've just kind of been quickly going through that. Now, so when we do our table, it is a two-way table. Uh-oh, that's not what I meant to do. Oh, I grabbed it. Okay, so I'm going to put, and we're going to put counts in here. Remember, you can put what? Probabilities, you can put percentages, or frequencies. Frequencies are just another way of saying the number of, right? Or counts. So let's put our face cards for along this way, and we'll say yes to face cards, no to face cards. Let's put our reds over here, and let's just say yes. I'm in your way, I know. Okay, here we go. Here we go. Now, we need totals too, don't we? So this will be our total. And then we'll also have a total over here. Okay, how many face cards do we have total? What do I put here? Aren't 26 yeses and 26 nos? And that makes our 52. How about reds? How many are yeses?
Wait, isn't the red 26 and 26 and the face
Oh, I flip-flopped the labels, didn't I? I flip-flopped the labels. You are right. This should be split differently. Thank you for pointing that out. So let's just take that information I just put in the wrong spot in the right spot. There you go. Thank you. Okay, now, so for the face cards, how many do I have? 12 face cards, and that means, huh? 40, very good. 40 would not be face cards. We need to fill in all the joint cells. Remember, these are our joint cells? Okay, these are our marginal counts. You'll need to write this down because you may see this terminology somewhere. Marginal counts just mean row or column totals. Okay, this number is kind of interesting. It's what? A table total. It's the total in your population or whatever you're looking at. Table total. Now, these up here are going to be your joint cell counts. They represent your intersections. Intersections mean A and B, correct? Okay? So, how many are yes and yes? It's those guys right there, correct? Those in the middle. 6. So how many say yes to face cards but no to reds? 6. Nope. Did I flip it again?
Exactly 20, and then the one below, yes, 6.
What?
The other 6 goes below the 6.
Yes, it does. Because that's going to be red no, but face card yes. So red no is this 6 right there. Okay? And then we have face cards no would be how many? 20. And then what? And then 20. So let's be clear. This 20 right here is no to both. So it's the intersection of no and no. Now, let's do the same problem using our probabilities. The probability of a face card or a red card is going to be the probability of a face plus the probability of a red minus the probability of a face and red. So what's the probability of a face from what we see here? It's going to be what? 12 out of 52. What about the probability to be red? Y'all stay engaged. What are you thinking? 26 out of 52. Very good. The problem is this. Look at what I've done. I'm saying yes to this and I'm saying yes to this. I have double counted this guy right there. That 6 is in both places. But guess what? The 6 really only, those 6 cards are physically only in the deck once, right? So you can't count them twice because it misrepresents the probability of selecting them. So I have to subtract out this 6 like this. Okay, so I need to introduce a new term. It's called mutually exclusive. In this case, do you see that those events are not mutually exclusive? You can have an overlap. Mutually exclusive just means no common elements. So it could be things like a red card and a black card. If I did a Venn diagram for that, let's see what happens. Just very quickly. So I've got red, I've got black, I've got 26, I've got 26, I've got 0. There are no common elements. These events are what?
Mutually exclusive.
Very good. Have y'all heard that term before?
Yes.
So events red and black.
So does that mean you don't subtract?
Okay. You don't need to subtract. So I don't need that last little bit of the equation. So this is how it kind of modifies it. It's going to basically say, I needed or, not and. Probability of A or B is just equal to the probability of A plus the probability of B. And guess what? I don't need to subtract because there's nothing there to subtract. Now, if I couldn't remember, if I set it up to subtract, I'd be like, oh, well, wait, there's nothing to subtract. That's because they're mutually exclusive. So I always tell students it's easiest to remember the main formula as this one up here. And then what do you do to modify it when you have mutually exclusive events? You're subtracting 0, or the probability would be 0. Okay? Now, you have a little sheet there with some problems on it. We are going to do, quickly, do number 1 quickly, because that one's pretty straightforward. 1, 3, 4, and 7 are the ones we're going to do. Okay. Is everybody with me? Guys, if you ever feel like you're just getting lethargic, it's late in the day, it's warm in here, just go get a sip of water. It'll wake you up, motivate you. All right, number 1. A bag contains 3 blue marbles, 5 red marbles, and 4 green marbles. You choose a marble without looking. What is the probability that you choose a red marble or a green marble? So isn't this the probability of R or G? And that'd be the probability of R plus the probability of G. Now, you probably did this all without any formulas. Do I need to subtract, first of all, before I move on? No, because they're totally separate events. You can't be red and green at the same time. So, what is the probability of red?
5.
So, there's 5 reds. How many greens? 4. How many total?
12.
Okay, so it's just going to be 9 over 12, and you just simplify that down. So that's number 1. Yes?
So this would be like an independent event and not like...
Okay, I am so glad you asked that question. This is such a hard concept for students to understand. Students think mutually exclusive and independent kind of mean the same thing. Mutually exclusive is when you're trying to find an or. Dependency is when you're doing an and. Okay, but listen, if you have 2 events that are mutually exclusive, guess what they will always be? They will always be dependent. Remember what dependency means. If you know a certain outcome has happened, does it tell you something about the other outcome? Or the other event, I should say. So knowing that you got a red marble tells you exactly what the probability to get a green marble is. 0. So it's kind of a weird thing. We don't really test you much on that in here. In AP Stats, though, it's a big concept we talk about a lot. Okay, number 3. Go ahead and do number 3. It's a little bit harder, okay? But again, that is what students think. They think mutually exclusive means independent. 2 different concepts, and I will go over that on Monday. And A, E, I, O, and U are the vowels we're going to use.
Miss Morgan,
Uh-huh.
Do we always draw the Venn diagram? Because like for this one, I could just do it by just counting the letters, and then I just wrote it out. So do we always have to use the formula?
You do not always have to do a Venn diagram, but for students that are struggling processing it in their heads, a Venn diagram might be helpful. And you can actually even put the specific vowels like A, E, I, O, U and like put them in the right spot. So for some students it is very helpful. Okay, so let's use the formula and then, but do we need the formula if we have the Venn diagram? That's the other thing. The Venn diagram makes it where you don't really need the formula. I can just literally count. Aren't there 10 out of 26? Okay, so let me kind of show it to you both ways. I have the probability of a vowel, or, let me make this more like a V, or a letter from the word geometry. So it's a probability for a vowel plus the probability for a letter in the word geometry minus any that are in both. What's the probability to have a vowel? 5 out of, and these are all going to be over 26. What's the probability for a letter in the word geometry?
10.
Okay, if you have a letter that repeats, you're not going to consider that letter here because what are you doing? You have 26 tiles, and whether you get an E out for this first E or for the second E, it doesn't matter. You still have the same probability of getting an E as you do an O or anything else. Kind of tricky, isn't it? So you really only have how many? 7. 7 unique letters. And then what would I do? Subtract out the elements that are in both, so 2, and that gives you what? 10 out of 26. Now, so do you see? You could have gotten the answer by doing a Venn diagram, adding the 3 and the 2 and the 5 together out of the universal set of 26 letters. Or you can use the formulas like I did there. You can do it either way. Or you could do it in your head. If you can do it that way, that's fine. Okay? Number 4. This one we might want a sample space. Yeah, you actually need a sample space on this one. So go ahead and take a minute and start drawing that out. I'll do it up here. Don't look at mine until you've at least tried it on your own. And remember now, these are sums, not products. So now we're adding. Okay, now, I'll try to find it. Okay, so for number 4, I want the probability the sum of the numbers rolled is even or greater than 9. So how many evens do I have? Because I need the probability of even plus the probability that the sum is greater than 9 minus, and I'm running out of space here, I would subtract out what? The probability that a number is even and the sum is greater than 9. So I'm going to physically show you how I'm double counting some of these. So where are my evens? So like 2, 4, 6. I'll just kind of dot them real quick. Can you see there's how many? I'm visually doing this for you so that it will make more sense.
I thought that it meant even to 9.
What's that?
I thought that it meant even to 9, so I figured out like even to 9, not even numbers.
Oh.
So I just read the problem.
Okay, yeah. I got you. That makes sense. But how many are there guys?
18.
18. So you can physically see the 18 that I have, right? So the probability, and all this is going to be over how many outcomes? 36. So I have 18 evens plus how many that are a sum greater than 9. So let's do that. And I'm going to do a little pink one for that. Where are my sums greater than 9? These, right? They have to be greater than 9, not equal to 9.
I multiplied, sorry.
Yeah, because we've been doing a lot with products. So sum is when you're going to add. So yeah. All right. So how many had sums greater than, or how many of our outcomes had sums greater than 9? 6. So I'm going to add 6 here over 36. But guess what I did? I double counted some of these. They're going to be the dots where the pink and the yellow overlap. I should have used like 2 colors that like make another color. That would have been cool. So it's going to be how many? It's not all the pink ones. It's just 1, 2, 3, 4. So I'm going to subtract out the 4 here. So I'm going to get what?
Oh, 24 over 36.
Okay, very good. So 24 over 36. So that's going to simplify down to 2/3. Okay, so that's number 4. Number 7. And I don't know why this writes over this. I don't know what that's doing. Okay, go down to number 7.
What is it, 20 over 36?
Yeah, not 24.
Oh, wait. What did I just do? I'm going to, hold on. Because this should have been 4.
Yes, and that's.
Oh, yeah, it is 20 over 36. So sorry. Somebody said 24 and I just wrote it. Okay. Alrighty. So that's going to simplify down to what? 5 over what? 9? Okay, good. So do number 7. Seven is important because it shows you how to do all this with a table. You have to practice this so you know when is it looking for just one cell over the total? When do you have to look at multiple cells? That kind of thing. So what's the probability that this student is a senior?
2 into 2 over 8.
Okay, yes, I'm only looking at this column total, 202 over 8 over 8. I'm just going to leave it as that. I'm not going to simplify. The student is a girl. I look at the row total for girls is what? 412 over 808. What about the student is a senior and a girl?
108.
Very good. So this is looking for the probability senior and girl. So that's the intersection, which is 108 over 808. And then when I look for the probability that a student is a senior or a girl,
614.
so senior or a girl, is going to be the probability of a senior plus the probability of a girl minus the probability that you are a senior and a girl. Yeah, it's all those numbers they just gave us. So 202 plus 412 minus 108. Why do we have to do that? Because if we do our girls here, y'all listening? Our seniors here, this is the problem. I counted the senior girls, I counted them twice when they physically only exist once. Okay, next page. I know I'm going kind of quickly here. Okay, on the next page we are going to do number 9. And we're going to do it pretty quickly. Guys, you remember I talked about this early in class. Your homework is actually in the textbook. And the optional homework is if you want to get started on the review, is you're going to pick it up when you walk out the door. It's over here. There's 2 different, there's the formula card and the review. Okay, fill in your Venn diagram and also think about the sample space that you would have, or not the sample space, the universal set you would have. Because some of those people didn't buy pizza or use a credit card. Okay. Now, and I know I'm going quickly through this. here is a strategy if you're struggling with this, because some students really do struggle with this. Start by just writing in place what they tell you is happening. So in other words, there's 220 people. So I know there's 220 in my universal set. Now they're not all going to stay down there because some of them are going to eat pizza and some of them are going to use credit cards. So, but I'm starting with that, so I have kind of like a placeholder for them. Now, it says of those, 104 bought pizza. So this is our pizza one, so let's say 104 here. Now, is that correct?
No.
With what I have read so far, it is correct. But in a minute, I have to adjust it, okay? So, and then it says 82 use credit cards. So far, it's correct. Half of the people who bought pizza used a credit card. So these 104 still bought pizza, but we know now half of them also use a credit card. So what you want to do is take half of that, which is 52, and move it there. But guess what is wrong with that? Is this is too big. So I have to go back to what? Just 52. Now, do I have 104 people in the pizza? Yes. What do I need to do here as well?
Minus 52.
And what would that give me?
30.
30. So this is going to be 30. All right, great guys. Y'all have a good weekend. So the probability would be.
Is it 30 over 220?
It'd be 52 plus 52 plus 30. Like that.
Yeah, I feel bad.
Is that what y'all got?
Don't you have to subtract the...
Not when you're looking at it like this. Let me show it the other way. So I would do 52, wait.
Well, no, because it says or use your credit card.
So really,
Oh.
aren't I looking for this sample space?
Yeah.
Now this is not right down there. How many total do I have?
Oh.
How many total would I have down here?
186. Well, no, 186 minus 220, so...
What?
220 minus 186.
52 plus 52 plus 30. Yeah, it's 220 minus 134. So that's going to leave me with 86. Is that what y'all got?
No, because... 104.
Okay, the 104 plus 82 minus 52. And here's the thing. These are going to give you the same answer.
It's really not that bad.
So this is 134 out of 220. And this is also 134 out of 220. Does that make sense? You can either use the Venn diagram and use this, and this separate, or you can use your overall possibility. Guys, hold it down, please. Like 104, 82, and then subtract out the overlap.